we're considering the question of what the maximum of this function is on this system, we've been practicing graphing systems. So what we'll do is we'll graph this system, and then we'll look at all the points that solve the system and consider for each point what the value of this function is, and try to find the maximum value of the function. And luckily we have already graphed the system right here. Here's the graph of the system. To be able to fit this graph onto the board, I had to switch my axes up a little bit. This is no longer the y-axis. I moved the y-axis over to here, so ignore this. Y-axis, x-axis. And then we've graphed the region that satisfies that system. And how many points are there in the region? Well, there's infinitely many points. And if we consider all of those points, it's going to take us all day to plug them in there, a lot of days. So we're going to try to figure out how we can do this without having to try every single one of those infinitely many points. And if you remember, back before, when we had these questions, when we tried to figure out what this looks like, ax plus by plus cz equals d, when we graph it, we started by looking at this. And to understand what this looks like when graphed, we drew our y and z axis, and the x-axis was coming out of the board, and we took cuts of this where we plugged in x equals 0, and we looked at what we got. And if you put x equals 0 in here and you solve it for z, then you get z. So if x is 0, then you get z equals 1/3 y plus 3. And so that's this line right here. And then if we did another cut, 1 inch where x is now 1 inch out from the board, then you get another line. It ends up being exactly the same slope, but 1 higher on the value here. So it moves up 1, and then if you do it 1 more out, it's 1 higher again, and higher again, and higher again. And if you put all of those cuts together, you can see that this is actually going to be a plane. And that strategy of taking cuts like that is generalizable, and you can see that actually anything that's in this form is going to be a plane. So knowing that, it tells you something about what this looks like when you graph it. If you see, this is in the same form as this. If you solve this for z, you'll end up with something that is in this form here, where you have a coefficient in front of x, in front of y, and then a constant term. So let's try and look at this in 3D now and see, knowing that the graph of this is a plane. So if we pull this out and rotate it, now that's a little tough to see. Let me do it again. You can repeat on the video, but remember the x-axis is pointing to the right and the y-axis is pointing up right over here. Here's the y-axis. Watch. Now the x-axis is coming out from the board. The x-axis is coming out from the board. The y-axis is going that way, and the z-axis is going up right here. So there's our z-axis. And now we think about all of the values of z on that region. So it would be distances up on the region. And I've plotted the coordinates of those points as heights on that graph. And if we think about what that region, the heights of all those points in that region would look like, well, there's a question. If it was a plane, when we look at it, we can see that the highest point on the plane is going to have to be at one of those vertices. Whereas if it wasn't a plane, it could be right in the middle of the region here. You can see that the highest point is actually right here. So it's only because the graph of this is a plane, like this plane right here, that we know that the highest point in the region has to be one of the vertices of the region. Thanks, Rob.